Okay, welcome to rate of reaction, so topic 3.4, and in this topic we're starting to have a look at some new key ideas. So we need to be able to have a look at and identify the time taken for a reaction to reach a particular point in the reaction. So we'll use this by determining different conditions and using data that we've been given to determine this. We also need to have a look at different times can be taken, so things like concentration, and you know this, so the amount of the reactants that we put in will determine how fast it happens. The temperature, so if we heat things up, things are likely to go faster. The pressure, which works equivalently to concentration, and the state. So when we're talking about the state, we're talking about gas, so gas, liquid or solid, presence of catalysts, and light can also work in a similar way to temperature, and you'll know this from things like photosynthesis. And finally, you need to be able to draw and interpret energy profile diagrams. So let's take a look at what this looks like in practice. The first part we'll have a look at is time taken to reach a specific point. I've got an example of a reaction occurring. So one that you haven't seen before is the iodine clock. Now this is a complex reaction because there's a two-part process, but we can determine an end point of this reaction by the colour change. The other one that we can take a look at is the sodium thiosulfate reaction, and this is one of the ones that you will be having the option to do for the design prac. So let's take a look at this in action now. Okay, so what you should have seen there is a reaction of the colour change occurring. If we change the concentration, we can change the amount of time it takes for that reaction to occur according to the rate of reaction theory. So we will increase the number of collisions per unit time if we increase the concentration, therefore increasing the rate that reaction occurs at and decreasing the total time for the reaction to occur. So this time we're going to have a look at it in terms of a graph. So we're actually going to be able to plot the time the reaction takes, or the concentration of the reactant or product, depends on which one we're having a look at, against time. And then we're going to be able to interpret what that graph is saying. So in this case, we're going to have a look at calcium carbonate reacting with hydrochloric acid. So we're going to measure the amount of carbon dioxide being lost, and we're going to do that by having the reaction on a scale. So let's take a look at that in practice. So you can see here we've got calcium carbonate chips, so let's take a look at those. So we can see the calcium carbonate chips here. We can see the hydrochloric acid on the scale, so we've got a set of scales here. And what you can see is about to happen is we are about to get the hydrochloric acid being poured onto the calcium carbonate chips. So what we know is we've got the mass of all of those things on the scales, and what we're going to be able to see is how much carbon dioxide is lost. Therefore, we're going to be able to graph the loss of carbon dioxide over time. So we've got a stopper in there in the form of cotton wool, just so that we know nothing else is getting added to that flask. So over time, you can see the scales going down. So we can see that we are losing carbon dioxide, and we can also tell by the fizzing that we have a reaction taking place. And here we've got a graph of that in action, and we can see that we've got different size marble chips, and that with the larger marble chips we can see that this graph is not as steep. So taking a look here, we've got quite a shallow graph compared with the small marble chips. So in the small marble chips, this goes up significantly steeper and then plateaus out, whereas the larger marble chips takes longer. What we can see is that surface area makes a difference to the rate of reaction. We would also see something similar happening if we had a higher concentration of the hydrochloric acid, so we would see a graph similar to the smaller marble chips. So we can see that at this point here, we've reached equilibrium. We can see that the reaction has stopped, so it fits in with point C, and that means that we've used up one of the reactants. So we've either used up all of the hydrochloric or all of the calcium carbonate. And if we have a look at the steep slope here, that fits with A, and we can see that we've got at this point in time a really high concentration of the reactants and a really low concentration of the products. And point B on the graph, when it starts to get a bit shallower, we can see that there's a longer time interval, so the slope at any one point is less, and therefore we've got a higher concentration of the products and a lower concentration of the reactants. So at this point in time, we've got a really steep instantaneous slope. Therefore, we've got a high probability of successful collisions. Here we've got a lower slope, and finally we have pretty much a horizontal slope. So we're saying that no more reaction is taking place. Here's an example of a type of question you could be asked. So we could be asked to write an equation for this reaction. So you saw the equation on the last slide with the hydrochloric reacting with the carbonate. Oh, sorry, in this case it's hydrogen formed with zinc. So let's have a look at hydrogen and zinc. So we've got hydrochloric acid reacting with zinc metal, going to form zinc chloride and hydrogen gas. Alright, so we just need to go through and balance that, and we need two of these. So there's our reaction equation. Obviously you'd write that quite a bit neater and on the one line. So we could draw a graph of the volume of the hydrogen on the vertical axis against time. So I've done that here for you, and you can see it looks pretty similar to the last graph you saw. Now, if we were going to explain how this rate changes with time, we can see that it starts off at a fairly fast rate, slows down, and then at this point in time we would say that the reaction has stopped, which would answer part D, and we'd probably say that it starts to become horizontal, which is when we'd say it stops at 400 seconds. And if we have a look at the table, you might see that I haven't drawn this quite as accurately. We do get two lots of 80. So we get 80 at 350 and then it stays 80 at 400. So maybe we could even say at 350 it's when it stops. So finally, this triangle represents the instantaneous slope. So if you were asked to find the rate of reaction at time equals 150, this is the triangle that you would draw. So you're going to draw it so that it comes out until we get to the vertical lines that we can measure, because that's actually easier for us. But we're going to make sure that we draw a tangent line, which is this touching line to the graph, at the point of time that we want to determine. So that's the instantaneous rate at that particular point in time.